Think about, that moment you flick a switch and a light comes on. Or maybe how a magnet just snaps onto your fridge door.
Hmm.
They seem like everyday things, right? But they really hint at these powerful, unseen forces working all around us.
It's fascinating, isn't it? How electricity, like powering a bulb, and magnetism, the stickiness you mentioned, they seem so different,
Yeah.
but they're actually, well, deeply connected. Two sides in the same coin, really.
Exactly. And that connection is precisely what we're diving into today. We're going to explore the essential ideas behind electromagnets and how they link up with other magnetic and electric stuff.
Right.
We've got some great educational materials to guide us. They've got diagrams, activities, the whole deal. Think of this as like your clear path to really getting these core concepts.
And it's not just about textbook definitions, you
Yeah.
know. Understanding this stuff helps you see how, well, basically everything works, from
Yeah.
simple gadgets right up to complex medical tech. So our goal here is to make it clear, engaging, hopefully give you a few aha moments without drowning you in jargon.
Okay, sounds good. Let's start right at the beginning then. What exactly is an electromagnet?
Okay, so fundamentally, an electromagnet is a temporary magnet. The sources define it basically as a piece of soft iron
Sorry, okay.
with insulated copper wire wound around it, or you could say any coil-carrying current that's wrapped around iron.
And the key word there is temporary.
Absolutely crucial. It's only magnetic when the electric current is actually flowing through that wire.
Right.
Cut the power and poof, the magnetism is gone instantly.
Okay, so that insulated wire you mentioned, what's its specific job? And why soft iron for the core?
Good questions. The insulation is, well, vital. It stops the turns of the wire from touching each other electrically.
Oh.
If they touched, the current would just short circuit, take the easy path,
Yeah.
and you wouldn't get much of a magnetic field.
Makes sense. And the soft iron.
The soft iron core acts like an amplifier for the magnetism. Soft iron magnetizes really easily when there's a current nearby.
Mm-hmm.
So it massively boosts the magnetic field the coil creates, makes it much stronger.
Got it. Now, our sources show two main shapes, bar magnets and U-shaped or horseshoe magnets, figures 13.2 and 13.3. How are those actually put together?
Sure. So for a bar electromagnet, like in figure 13.2, you start with a straight bar of that soft iron.
Right.
Then you wind the insulated copper wire tightly around it, connect the ends of the wire to, say, a battery through a switch,
Okay.
close the switch, current flows, and boom, the whole thing acts like a magnet.
The iron bar becomes temporarily magnetic.
And it has poles, right? North and south. I remember reading the current direction matters there.
You remembered correctly. That's a key point. Which end becomes north and which becomes south depends entirely on which way the current is flowing in those coils.
How so?
Well, you look at one end, and the current seems to be going around clockwise. That end becomes the south pole.
Clockwise is south.
Okay.
And if you look at an end and the current appears to be flowing anti-clockwise, then that end becomes the north pole. Figure 13.2 shows that pretty clearly.
And the U-shaped one in figure 13.3, same idea, just bent.
Pretty much, yeah. You take a U-shaped piece of soft iron, wind the insulated wire around it,
Mm-hmm.
connect it to a power source via switch, turn it on, current flows, you get a magnetic field.
And the poles are at the ends of the U.
Exactly. And again, the direction of the current flow determines which end is north and which is south, just like with the bar. Clockwise for south, anti-clockwise for north when you're looking at the pole face.
The materials also mention a really simple experiment, Activity 1, figure 13.4, using just an iron nail, wire, and a battery to pick up pins.
Ah, yes, that's a classic. Great way to see it in action.
It says using a battery makes it stronger than just a single cell. Why is that?
Well, that activity really shows the temporary nature, doesn't it?
Mm-hmm.
Wrap the wire, connect the cell, the nail picks up pins, disconnect, pins drop. A battery usually provides a higher voltage than a single cell. More voltage means more current pushed through the wire.
Ah, okay.
And more current means a stronger magnetic field. So the nail can pick up more pins. It directly shows one of the ways you can control the strength.
Which leads nicely to my next question. What are the main things that control how strong an electromagnet is?
Good transition. The sources point to two main factors. First, the number of turns in that coil of wire.
More turns.
Stronger electromagnet, fewer turns, weaker magnet. Pretty direct relationship.
Okay, makes sense. What's the second factor?
The second one is how much electric current you pass through the coil.
So more current.
Also means a stronger magnetic field, less current, weaker field.
So you can easily adjust the strength, unlike a permanent magnet.
Exactly. That adjustability is a huge advantage for electromagnets in, well, loads of applications.
Yeah, let's talk about those uses. I was quite surprised by how long the list was in the materials. They seem to be everywhere.
They really are. They're hidden inside so many things you use daily. Think about electric bells, fans, electric motors.
Mm-hmm.
All rely on electromagnets.
Okay, common appliances. What else?
Then there are the big industrial uses. Lifting huge piles of scrap iron and steel. Imagine giant electromagnets on cranes.
Wow. Yeah.
Also, removing tiny bits of iron from wounds. That's a medical use.
Really? From
Yeah.
wounds, that's specific.
Yeah, very precise. Also, loading furnaces with iron, separating magnetic ores in mining.
Separating ores, okay.
The source even mentions treating certain medical conditions, though it doesn't say which ones. And interestingly, they're used to make strong permanent magnets, too.
Making permanent magnets using temporary ones.
That's interesting.
It is, isn't it? It kind of highlights the difference between them.
Which is a perfect segue. The materials have a table comparing permanent magnets and electromagnets. What are the key takeaways there?
That table's useful. It boils down to a few key differences. Permanent magnets, well, the name says it all. They keep their magnetism.
Right. Fixed strength, fixed poles you can't easily change which end is north. And they're generally weaker at magnetizing other things.
Okay. And electromagnets.
They're the opposite in many ways. Temporary magnetism only works when current flows.
Mm-hmm.
But crucially, their strength is variable. Change the current or turns.
Yeah.
You can also reverse the poles just by reversing the current direction.
Ah, controllable.
Very controllable. And they can be made incredibly strong, much stronger than typical permanent magnets while they're on. So it's a trade-off. Permanence versus control and potential strength.
Okay, that makes sense. Now, one device that uses this on-off control really well is the electric bell. Figure 13.5 shows how it works. Can you walk us through that?
Ah, the electric bell. It's such a clever application of basic electromagnetism.
Yeah. How does it work?
Okay, so you've got a U-shaped electromagnet, then there's an iron armature, just a piece of iron with a little hammer attached to it.
Okay, hammer and a gong.
Yep, a gong for the hammer to hit. And then there's a contact screw and a spring. So when you press the bell button, you complete the circuit. Current flows through the electromagnet's coil.
Making it magnetic.
Exactly. The electromagnet attracts the iron armature. This pulls the hammer over, and ding, it hits the gong.
Ah, but does it just ring once?
No, here's the clever bit. As the armature moves towards the magnet, it actually pulls away from the contact screw,
Oh, I see.
and that breaks the circuit. The current stops flowing to the electromagnet.
So the magnetism disappears.
Instantly. The electromagnet lets go of the armature. The spring then pulls the armature back to its original position.
And that touches the contact screw again.
Precisely, which completes the circuit again. Current flows, electromagnet attracts, hammer hits gong, contact breaks.
And the whole cycle repeats over and over.
As long as you hold the button down, yeah. It's this rapid on-off cycling, this self-interruption that creates the continuous ringing sound. A really neat mechanism.
It really is. Okay, so that's a practical application. Let's zoom out a bit to the fundamental link between electricity and magnetism. The materials credit Hans Christian Ørsted with a key discovery back in 1820. What did he find?
Ørsted's discovery was, well, monumental. He observed that an electric current flowing through a wire creates a magnetic field around that wire.
Which people didn't know before.
Generally, no.
Yeah.
Electricity and magnetism were thought of as separate forces. Ørsted showed they were intimately connected. If you have moving electric charge that's current, you get magnetism.
Mm-hmm.
And the study of these magnetic effects caused by electric currents is what we call electromagnetism.
And the source details a couple of experiments, figures 13.6 and 13.7, that show this link. Can you describe the first one, the compass?
Sure. Experiment 1, figure 13.6, it's simple but profound. You place a compass needle near a straight wire.
Okay.
With no current in the wire, the compass just points north, aligning with Earth's magnetic field, right?
Right, standard compass behavior.
But then you pass a current through the wire. And crucially, the compass needle deflects. It moves away from pointing north.
Why does it move?
Because the current in the wire has created its own magnetic field, and that field is now pushing or pulling on the little magnet in the compass needle. It proves the current-generated magnetism.
Okay, clear proof. What about experiment 2 with the iron filings on cardboard?
Experiment 2, figure 13.7, gives you a visual map of that magnetic field. You poke a wire vertically through some cardboard, sprinkle iron filings on the cardboard, then run a current through the wire. What happens?
They form a pattern.
Exactly. The iron filings arrange themselves into concentric circles centered on the wire.
Oh, cool.
It beautifully shows the shape of the magnetic field lines around a straight current-carrying wire. They're circles.
And does the compass needle help here too?
Yes, if you place a small compass on those circles, it'll line up tangent to the circle, showing the direction of the field at that point. And if you reverse the current direction on the
The
wire,
compass needle flips around.
it does. Shows the magnetic field direction reversed too. The experiment also shows the field is strongest near the wire. The filings cluster more densely there.
Right, where the field lines are closer together. That makes sense. Now, just quickly, the source mentions ISI marks on appliances. Why bring that up here?
It might seem a bit random, but it's about safety and standards. The ISI mark, used in India, certifies that an electrical product meets safety and quality standards.
Okay.
Since we're talking about harnessing electricity and its magnetic effects in all these devices, it's, well, relevant to mention the importance of making sure these things are built safely and work efficiently. It's about applying these principles responsibly.
Got it. Safety first. Okay, so we know current makes a magnetic field. How do we figure out the direction of that field? The source gives two right-hand rules.
Yes, these are handy mental shortcuts. The first is the right-hand thumb rule, shown in figure 13.8.
Okay, how does that work?
Imagine you grab the wire with your right hand, point your thumb in the direction the electric current is flowing.
Right thumb follows current.
Then the way your fingers naturally curl around the wire, that direction shows you the direction of the circular magnetic field lines.
Ah, okay. Thumb for current, fingers for field direction. Simple. What's the other one? The corkscrew rule.
The right-hand corkscrew rule, figure 13.9. Similar idea, different visual. Imagine you're screwing a corkscrew into, say, a piece of wood using your right hand. The direction the corkscrew moves forward represents the direction of the current in the wire.
Okay, screw moving forward is current.
Then, the direction your hand is turning the corkscrew to make it go forward. That rotation direction represents the direction of the magnetic field lines circling the wire.
Got it. Two ways to visualize the same relationship.
Exactly. Pick whichever one makes more sense to you.
All right. Let's move on to solenoids. What are they exactly? They sound a bit like electromagnets.
They're very similar. A solenoid basically is just a long coil of insulated wire, wound tightly, often on a cylinder, maybe cardboard or maybe soft iron.
So like the coil part of the electromagnets we discussed?
Precisely. Sometimes solenoid implies just the coil, maybe with air inside, but if you put a soft iron core inside a current-carrying solenoid,
It becomes a much stronger electromagnet.
you got it. The iron core concentrates the magnetic field lines, making it powerful.
So a solenoid with current flowing through it also creates a magnetic field, like a bar magnet.
Absolutely. It behaves very much like a bar magnet. It has a definite north pole at one end, a south pole at the other. The magnetic field lines loop out from the north, around to the south, and pass through the inside of the coil, too.
Okay. And how do we know which end is north and which is south on a solenoid? There's another rule, the clock rule, figure 13.10.
Yep, the clock rule. Another handy rule for polarity. You look at one end of the solenoid coil.
Okay, looking at the end.
If the current in the wires you see on that end face is flowing in an anti-clockwise direction, think of the hands of a clock going backwards.
Anti-clockwise.
That end is the north pole.
Okay, anti-clockwise north, so clockwise must be.
South pole. If the current appears to flow clockwise when you look at the end face, that's your south pole. It ties back to how poles were determined for the bar, and U-shaped electromagnets too.
Right, it's all consistent. Okay, moving forward. The source talks about a force acting on a wire carrying current inside a magnetic field. Figure 13.11 illustrates this. This sounds really important.
Oh, it is. Hugely important. This is the flip side. In a way, we know current makes a field. This principle says if you put a current-carrying wire into an existing magnetic field, the wire experiences a physical push, a force, as long as the current isn't perfectly parallel to the field lines.
A force on the wire itself.
Yes, a mechanical force.
Yeah.
And its direction is perpendicular to both the direction of the current and the direction of the magnetic field.
Perpendicular to both.
Okay.
And if the current is parallel to the field?
Then, interestingly, no force. The effect depends on the current cutting across the magnetic field lines.
And this force. This is what makes electric motors turn, isn't it?
You hit the nail on the head. That fundamental interaction, a magnetic field pushing on moving charges, the current in the wire, is exactly how electric motors generate rotational motion.
Amazing. So current makes magnetism, and magnetism exerts a force on current.
That's the essence of it.
Yeah.
And now, let's talk about going the other way, using magnetism to make electricity.
Right, the reverse process, generating electricity from magnetism. This is electromagnetic induction, Faraday's work.
Precisely. After Ørsted showed electricity makes magnetism, Michael Faraday, among others, thought, okay, can magnetism make electricity?
And could it?
Yes. In 1831, through some really key experiments, Faraday demonstrated what we now call electromagnetic induction.
Okay, the source describes one of those experiments in figure 13.2, a magnet, a coil, and a galvanometer that's a current detector, right?
Exactly, a sensitive one. So you connect the coil of wire to the galvanometer. If you just hold a magnet still, near or inside the coil,
Nothing happens.
nothing. Galvanometer shows zero current. But the moment you start moving the magnet, pushing it into the coil or pulling it out,
Ah,
the galvanometer needle jumps. It shows a current is flowing in the coil.
wow. Just from moving the magnet?
It's just from the relative motion. And what's more, if you move the magnet out instead of in, the current flows the other way. The galvanometer deflects in the opposite direction.
Okay, direction of motion matters. What if you move the coil instead of the magnet?
Same result. If the magnet's still in the coil and you move the coil towards or away from it, you also induce a current.
So it's not about which one moves, but the fact that there's movement between them.
Exactly. It's the relative motion that counts. As long as magnetic field lines passing through the area enclosed by the coil are changing, you induce a voltage, and if the circuit's closed, a current.
And that phenomenon is electromagnetic induction.
That's it. And the current produced is called the induced current.
Okay. What makes that induced current stronger or weaker?
Three main things, according to the source. One,
Yeah.
more turns in the coil. More loops cutting the field lines means more induced voltage.
Makes sense. 2.
Use a stronger magnet. A stronger field means a bigger change as it moves, so more induced current.
Right. And 3.
Speed. The faster the relative motion between the magnet and the coil, the faster the magnetic field changes through the coil, and the stronger the induced current.
More turns, stronger magnet, faster motion.
Got it. Now, this leads to AC and DC alternating and direct current. How does induction relate to those?
Well, imagine you keep moving that magnet back and forth, in and out of the coil, continuously.
Right, back and forth.
The induced current would keep changing direction, right? Flowing one way as the magnet goes in, the other way as it comes out.
Ah, constantly switching direction.
Exactly. That's alternating current, AC. It periodically reverses direction. That's the kind of electricity we typically get from wall sockets. The source shows the symbol for it.
Okay, and DC.
Direct current, DC, flows consistently in one direction, like the current from a battery. Doesn't change direction. The source gives symbols for DC too.
So induction naturally produces AC if the motion is back and forth or rotational?
Often, yes. Especially in generators. Which brings us to the dynamo, or electric generator.
Yeah.
That's basically scaling up this induction principle, right?
Precisely. A dynamo, or generator, is all about converting mechanical energy, like spinning a crank or a turbine, into electrical energy using electromagnetic induction.
How does it work, basically?
You have a coil of wire, the armature, often on an iron core. You make this armature spin mechanically inside a strong magnetic field.
Spinning coil in a magnetic field.
As it spins, the amount of magnetic field lines passing through the coil is constantly changing. Maximum when it's face on, minimum when it's edge on, then maximum again.
Right, constantly changing.
And the continuous change induces a current in the rotating coil.
Okay. And the components in figure 13.13, magnet armature. What are slip rings and brushes?
The horseshoe magnet provides the field. The armature is the spinning coil where current is induced. The slip rings are two continuous metal rings attached to the ends of the coil, spinning with it. The carbon brushes are stationary contacts that press against those spinning slip rings. They provide the connection to get the induced current out of the rotating coil and into the external circuit, like wiring to a light bulb.
Ah, they bridge the gap between spinning and stationary parts.
Exactly. Dynamos are a key way we generate electricity.
Okay, next up, transformers. These change AC voltage up or down, still using induction.
Yes, transformers rely entirely on electromagnetic induction, but in a slightly different way. They don't usually involve physical movement.
No movement. How does the field change then?
Because they work with alternating current. Remember, AC is constantly changing direction and strength.
Ah, right.
So a transformer has two coils wrapped around a common soft iron core, often laminated like thin sheets stacked together to reduce energy loss.
Two coils, primary and secondary.
Yep. The primary coil is connected to the input AC voltage. Because the input current is constantly changing, it creates a constantly changing magnetic field in the iron core.
Okay, changing field in the core.
And this changing magnetic field passes through the secondary coil, which is also wrapped around the same core.
And a changing field through a coil induces.
Induces a voltage. An AC voltage is induced in the secondary coil.
Clever. So how does it step voltage up or down?
It all depends on the number of turns in each coil. Let's say NP is turns on the primary, Ns is turns on the secondary.
Okay, NP&S.
If the secondary coil has more turns than the primary, NSNP, the induced voltage in the secondary, ES, will be higher than the input voltage on the primary. That's a step-up transformer.
More turns out, higher voltage out.
Exactly. And if the secondary coil has fewer turns than the primary NSNP,
And it's step down, lower voltage out.
you got it. The output voltage S will be lower than the input EP. The ratio is ES, NSNP. The source gives a couple of examples calculating this.
And these are used all over the place, right?
Absolutely essential. Power plants use massive step-up transformers to boost voltage for long-distance transmission. High voltage means lower current, less energy loss. Then, substations and those green boxes in neighborhoods use step-down transformers to bring the voltage down to safe levels for our homes.
Okay.
Plus, you find them in phone chargers, step-down, voltage stabilizers, even things like X-ray machines that need really high voltages step up.
Everywhere, basically. Okay, finally, let's loop back to electric motors. We touched on the principal force on a current in a field. Figure 13.15 shows a simple one. How does that force make it spin continuously?
Right, the motor converts electrical energy into mechanical rotation. You've got the armature coil again, sitting in the magnetic field of a horseshoe magnet.
Mm-hmm.
You feed DC current from a battery into the coil. Now, one side of the coil has current going one way, the other side has current going the opposite way relative to the field.
Okay, opposite currents on opposite sides.
So they experience forces in opposite directions. One side gets pushed up, the other side gets pushed down.
That creates a twist, a torque.
Exactly. That torque makes the coil start to rotate.
But how does it keep rotating? Wouldn't the forces reverse after half a turn?
Good point. That's where the split rings come in. Instead of continuous slip rings like the generator, a simple DC motor has a commutator, often a single ring split into two halves, insulated from each other.
Split rings. Okay.
Each end of the coil connects to one half of the split ring. The carbon brushes press against these halves. As the coil spins, every half rotation, the brushes switch contact from one half of the split ring to the other.
What does that switching do?
It reverses the direction of the current flowing into the coil at just the right moment.
So even though the coil has flipped over, the current direction relative to the magnets is switched, so the forces keep pushing it in the same rotational direction.
Precisely. It ensures the torque keeps acting the same way, giving continuous rotation. It's quite ingenious.
It really is. And motors are in, well, anything that spins using electricity.
Pretty much. Washing machines, fans, mixers, hair dryers, power tools.
Yeah.
Countless things rely on this principle to create motion.
Wow. Okay, so we've really covered a lot of ground, from the basic idea of an electromagnet.
Yeah, making temporary magnets with electricity.
Yeah. To how they work in bells, how current creates fields around wires, solenoids.
Then flipping it using moving magnets to induce current electromagnetic induction.
Which leads to generators and transformers changing voltage.
And finally, back to using the force between currents and fields to make motors spin.
It's amazing how interconnected it all is, this fundamental dance between electricity and magnetism.
It truly underpins so much of modern technology, things we just take for granted.
Definitely makes you look at everyday devices differently, doesn't it, seeing those invisible forces at work?
Absolutely. And maybe it prompts a final thought for you, our listener. We've explored this deep link between electricity and magnetism. What other fundamental connections, maybe even other unseen forces, could be shaping our universe that we're only just beginning to understand?
That's a big question. Or perhaps, now that you have this deeper grasp of electromagnetism, what kind of future innovations can you imagine these principles unlocking? What comes next? Something to think about.